So that's probably the fifth big section, which is called random current representation. So it's surprisingly a representation which is very often ignored, even by people working on the Ising model, and it's basically one of the most powerful representation to study at least the critical behavior of this model. So we are going to work with the Ising model today. And for the Ising model, when I take the measure on the graph G at inverse temperature beta, instead of putting one boundary condition, I would just say plus boundary condition. Okay, that's just the standard thing for the Ising model. And there is also the one with three boundary conditions. So remember the plus boundary condition, what you can do, you can take the random cluster measure and color the clusters. Well, you could do that with the infinite volume random cluster measure. It will give you an infinite volume measure, which I will call mu beta plus. So there is a notion of infinite volume measure for the Ising model. In fact, you can just check directly. You don't need the random cluster model to do that, but you could check directly that measures with plus boundary condition on finite graph, when G tends to ZD, just tends to a measure, which you call the infinite volume Gibbs measure with plus boundary conditions. And you can do the same if you take free boundary conditions. So these are standard things. I'm not going to spend time on it, but if you want to be convinced, just think you can get this by the coupling with the random cluster measure, because there we justified the fact that there is an infinite volume measure. Very well. I'm not going to restrict myself to nearest neighbor, simply because it's not going to matter at all in the different proofs. So I want to just illustrate the fact that it works in full generality. So I'm taking the Ising model and I'm taking even maybe long-range coupling constants. So remember that these guys are just depending on the difference y minus x, okay? They are translational invariant. And I'm going to also assume they are positive. So the model is ferromagnetic. So that's what I want to study. So what is this random current representation? So remember here just the last thing, just for those that were not there at the first lecture, the Hamiltonian is just going to be that. Okay? Okay, so what is the random current representation? So it's a very, very simple observation, which is based on the following fact. So our goal is to exploit the fact that exponential, you're going to be, it's very, very deep. Just we want to exploit the fact that this thing is simply the sum for nxy equals 0 to infinity. This is a variable of beta jxy times sigma x sigma y to the nxy divided by nxy factorial. Okay? I want to exploit this. This is my main idea. So in order to exploit that, I'm going to introduce the notion of current. So a current is just a function from ZD, let's say the pairs of elements in ZD, but unordered. Okay, so the subset of with two elements into the integers. This is just that. Okay, this is a current. So n. This is the definition of a current. Any function from pairs of points into the integers. Now for a point x, the set of boundaries or sources of the current would be what? It would be the set of x in ZD such that the sum over y of nxy is odd. Okay. So a priori here, I mean, it may be that for the current, I would have this thing would be infinite, right? Because I'm summing over every y. But concretely, what we will do, we will always work on finite subsets here. So we're going to take G, a subset of ZD, and in fact, maybe sometimes it will not be exactly a subset of ZD, but I will let you know exactly when. Okay, so then this thing completely makes sense. It's a finite integer, and when it's odd, I call it, I put it in this set, and I call it the set of sources. So you should really, I mean, why do we call it current? Because if you have no sources, you can see this set as somehow a union of loops, of a superposition of loops. And if you have sources, then you have path going from this source, I mean, one source to another one. So for instance, it's easy to check that you cannot have only one source. It's not possible. Okay, so the sources are paired somehow. So that's the denomination for current, and now we will sample currents uniformly, so I'm going to need the following thing. So for beta positive, I'm going to code W beta of n. The following thing is going to be the product over x and y of beta jxy to the nxy divided by nxy factorial. Okay? So it's basically this thing, except that, I mean, that's this term without that, and you do the product on every x and y. Once again, since we are in finite volume, this thing is well defined. So this is a current. Now, what is the connection with our model, with the Ising model? So the connection is going to be that if I look at the partition function, sorry? Exactly, yes. That's one of the corollaries, yes. So if you take a subset A of ZD or of V of G, so you have a finite graph G, you take a subset of the vertices. I'm going to define the partition function A like that as the sum over every sigma in minus plus to the V of G. So I sum over every configuration. I'm going to sum the exponential of minus beta times the Hamiltonian. So this is just a partition function, right? I'm summing all the weights of my configuration. So this is the partition function. But I'm going to put in front the product for small a in capital A of sigma A. Okay? This is just a definition. So for the empty set, I get the partition function, and for if I take the singleton, I'm going to get the sum of sigma A times blah blah. I mean, so now the proposition, which is the important one here, is that for every G subset, finite subset of ZD, for every beta positive, I have the following. I have that Z3 G beta of A, and so for every A subset of V of G, this thing, in fact, is simply the sum on the currents with sources A of W beta of n, and when I say it's simply the sum, I'm lying a little bit. There is the 2 to the V of G in front, to the number of guys in G. So there is a very simple representation of this sum in terms of sum of currents. So maybe before I prove that, I can already highlight something important, which is that imagine I want, for instance, to study, as I did with random current representation, if I want to study the spin-spin correlation. Okay? If I want to do that, well, I can simply notice that this spin-spin correlation, by definition, it's the sum over something, and the normalization constant is going to be this guy for, it's going to be the partition function. And at the top, what I'm going to sum is exactly this term. Right? This is going to be exactly the spin-spin correlation. But now you see that this representation tells me that somehow if I look at this thing, it is equal to the sum over sources, currents with sources x and y of W beta of n divided by the sum over sourceless currents of W beta of n. Okay? So if you do a picture here, what is happening? Imagine, so you have your graph G. You have x and y. So what is a current a priori? It's a superposition of loops. Okay? Maybe they intersect and so on. But you can see it as a superposition of loops. Sometimes you will use several times the same edge. This will correspond to the guys with nxy, for instance, equal to 2 here. There are 2 loops going through this guy, and so on. Now, if you have a source is at x and y, what is happening? Then there is no other way. You need to have a path going from x to y in this thing. So in some weak sense, we are getting something close to a geometric representation in the sense that we are looking somehow at the probabilities that x and y are connected in some kind of source, eddy currents, random currents. The thing is that, of course, I'm not summing on the same set here, so it's not really, you don't have a direct interpretation in terms of probability of some random, for instance, sourceless current. Okay, because here it's not sourceless current. But you are going to see that we are going to manage to twist a little bit that, and that in fact it's the square of this quantity, which is very well represented in terms of probability of something. And the square is going to come back later on in the yes. Okay, so maybe I should, so you see, since you have some of the nxy, since you have your nxy, just imagine it's superposition of edges, okay? If you have, say you take a sourceless current, okay? Take one edge for which nxy is positive, okay? Then there must be, at the end of this edge, so this edge arrives somewhere, there must be another edge with nxy positive. That's exactly what I'm trying to explain. I'm trying exactly to explain that. Okay? So take an edge and draw it. Then there must be another edge going away. There must be one of these edges with nxy positive. Okay? Because there is sourceless, so this guy, maybe it's this edge, then you go back. But take one of them for which is positive, go like that. A pair of points if you prefer, a pair of points. So to go x, y, and then there must be a z for which nyz is positive. Do like that, okay? So every time you draw this edge, you remove one to your current, okay? You do like that. At some point, you are going to close, because you are on a finite graph, you are going to close your loop, okay? Now you remove a certain number of 1 from your current, and you have once again a sourceless current, so you carry on. You take another point, and you do like that. You go around. Maybe you pass through the same thing, and you arrive here. And you do like that, and you are going to exhaust everybody. At the end, you drew a family of loops. There is no canonical way to do it. It's not canonical, but you can interpret that as a union of loops. Okay? And if you take the nearest neighbor model, then it's going to be really on edges. So that's why maybe, my tongue is a little bit. I'm used to the nearest neighbors, so then I say edges. But you are right that a priori it goes from x to y to any points. Okay. Yeah. Exactly. NXY is the number of edges between x and y. Yeah. Yes. Okay. So just the proof now of this thing. Yeah, I mean, I was really not clear on that. Sorry. So this proposition, how do we prove it? So we look at this thing. And the exponential of minus beta times the Hamiltonian, I'm going to just write it as a sum over x and y of e to the beta jxy sigma x sigma y. Okay? This is just the same thing. Now I expand. I use this thing. I use the expansion. So I get the sum over nxy equals 0 to infinity of beta jxy sigma x sigma y to the nxy divided by nxy factorial. Now I can exchange everything. I can try to put this sum out. So I'm going to get a sum over n, which are currents, of, well, you are going to have the product of the beta jxy to the nxy. So this guy is going to get the w, I mean, it's going to be the w beta of n. And then you have things that depend on sigma x and sigma y, which I'm going to sum. It's going to be the sum over the configuration. And what depends on that? Well, you are going to have a product over x in your graph. Sigma x appears how many times? Well, it appears exactly for every y nxy times. So it's going to be the sum over y of nxy. Okay? Except if x is in A, in such case, you add 1. So you have plus delta xi, delta of x belonging to A. Right with that? So it's just, I just exchanged the two sums. But now look at this. What is this thing equal to? Assume for a moment that one of these integers is odd. A configuration sigma always comes with a configuration minus sigma. So if this thing is odd for a certain number, then the things are going to cancel. So this quantity needs to be even for every number, and if it's even, then you are summing just 1. So you are summing over every configuration 1, you are just going to get 2 to the number of vertices. So this thing is equal to 2 to the number of vertices if sum over y of the nxy plus delta of x in A is even for every x, and it's 0 otherwise. So in other words, you get 2 to the number of vertices, sum of w beta n, and this is only if this thing is even for x not in A, and this thing is odd for x in A. So you exactly get that it's sources, I mean the currents with sources A. Okay? For people who saw the high temperature expansion of the model, I mean, it's a little bit reminiscent, except that you don't use the same starting thing. For the high temperature, you use the fact that this exponential, you can write it as a linear combination of cosh and sinh. And here, well, you do something a little bit more abrupt, and you just use a Taylor expansion. So this is for the free boundary conditions. What happened for the plus boundary conditions? Because we are going to work also with the plus boundary condition. So for the plus boundary condition, it's not going to be more difficult. It's just going to be a little bit different. What we are going to do is we are going to add a vertex delta, which is not in ZD. And we are going to call it the ghost vertex. And we are going to look, let's define G, for a graph G. Let's define Jx delta, which is going to be something that depends on G. I'm going to define it as the sum of a y not in G of Jxy. So interpret in some sense, so think you have your graph G. Outside of the graph, it's all pluses, okay? Well, somehow I want to contract all the edges outside the graph into one edge, all the vertices, sorry, outside the graph, into one vertex, which I'm going to call the ghost vertex. And so all the coupling constants are going to be sum, because for every x, the number, the interaction with outside was exactly the sum of this Jxy. So that's why I'm defining this Jx delta. So now I have this new ghost and I have this new coupling constant. I can define on G union this ghost, I can define the same random current. And what I get is that when I look at plus boundary conditions, property, if I take beta positive, G finite, and A a subset of V of G, I'm going to get that, that Z plus this time of G beta of A. So you guess how you define this. It's just the same as before, except that here you are taking the Hamiltonian instead of taking the free Hamiltonian, you are taking the plus Hamiltonian. Okay? Well, this thing is going to be the sum of the W beta of n as before, except that now you take, and also with currents with sources A, except that now here n are currents, is a current on G union the ghost vertex. Okay? So it's exactly the same. Compute the same quantity, it's the same sources, but this time on G unions the ghost vertex. Notice one interesting thing. If you look here, and you take just A to be even, to be odd cardinality, then you get 0 because there is no sources, there is no currents with an odd number of sources. And this is normal because you have a global symmetry plus minus, so this thing would be a 0. Here, for the plus boundary conditions, that's not what you expect because you have these plus boundary conditions which are breaking the symmetry. But now you can have an odd number of sources because delta could be your other source. You are not saying whether delta is a source or not. Okay? And the proof is exactly the same. You do exactly the same expansion. It works similarly. Very well. So this is the connection, and just one remark, trivial remark, that you can try to do it without that. By the way, I'm going to sigma A like that. Maybe that will be a convenient notation. Sigma A is going to just be the product of A in the set A of sigma small a. Okay? Well, just a remark is that you have that if I take the Ising model with some boundary condition, plus or free, then when I look at the average of sigma A, it's positive. Well, yes, because it's the ratio of two positive quantities. Right? Well, this is not trivial to prove directly. If you try to do it really by hand, it's not obvious at all, in fact. So this is called the first Griffiths inequality. We are going to see another one in a minute. So this is a very simple illustration that this random current representation, which is completely trivial to introduce, Well, it gives you immediately somehow a non-trivial fact on the Ising model. And now what I'm going to try to do is to extend a little bit what you can do with this random current and give you other inequalities and correlation inequalities for this model that you get just by observation. Once you have this random current, it comes even for free. I mean, almost for free. So that's a new section, which is applications to correlation inequalities. Correlation inequality. So I should say this is why it was introduced first, by Griffiths in particular. And it was made popular by Eisenman. I hope that at the end of the talk I will manage to tell you exactly what was the original paper by Eisenman that made it so famous. Okay. So this was just a straightforward application. Okay, you just observe that you are summing positive things. For the other application to differential inequality, to correlation inequalities, we are going to need a lemma, and that's going to be our main tool. I'm going to use it almost constantly. So this lemma is called the switching lemma. So what is it saying? It's saying take a function f from the set of currents into R. And let's look at two currents, N1 and N2, on G. In fact, one of them could be on G union delta, and I will use it like that, but let's just simplify a little bit the picture. Then we have the following. Imagine and let's take A, a subset of V of G, and X and Y, two elements of V of G. So what is the switching lemma? The switching lemma is saying, imagine I am summing over two currents, and I'm summing, the first current has sources X and Y, and the second sources A. And I'm summing W beta of N1, W beta of N2, and I'm averaging N1 plus N2. I mean, the function at N1 plus N2. So really imagine that as these are, after we will divide by some partition functions. So really think of, I'm taking two independent currents, and I'm looking at the function of the sum of the two. Well, the switching lemma is saying this is equal to the sum. So what you do is that you switch the sources from this set to this one. So you're going to put them down. So you are going to put N1 is going to be sourceless, and N2 is going to have sources A, symmetric difference XY. Maybe I should have taken X and Y not equal. Otherwise, it's trivial. Well, so then I don't need to do that. Okay, so you switch the sources, and what is the cost of that? So you are going to still have this quantity, but now you add something, and you can a little bit guess what it is. Here in N1, X and Y need to be connected. Here, a priori, they have no reason because maybe X and Y are already in A. So the thing that you're going to add is the indicator that X is connected to Y in N1 plus N2. So here I should tell you what I mean by connected because it's not really clear. For a current N, you can look at the trace of the current. Okay? So I'm going to take for a current N, you're going to get the trace of the current. It's one. Between X and Y is going to be 1 if there is an edge. If it's positive, and 0 otherwise. Okay? And really think like there is an open edge between X and Y, or there is no edge between X and Y. So I want it to be connected in N1 plus N2. Okay, so that means that I can go from x to y through a path for which I'm always using pairs of points for which n1 plus n2 is positive, strictly. So the proof is not very enlightening, but since I guess we have time, I'm going to present it for completeness. It's completely combinatorial. There is nothing hidden there. So let's try to do it. I'm not guaranteeing full success on this one. Very well. So what we are going to do first is that we are going to reindex the thing. So we are going to write m to be n1 plus n2, n1 to be n. Okay, so I'm changing the summation. So if I sum, let's call it 1. So if I sum 1, if I rewrite it in terms of m and n, you can check, it's a very simple thing, that you get that, well, m is the sum of the two, so the sources is going to be a symmetric difference with x and y. And then what you're going to get is you are going to get f of m. Well, this is obvious. Okay, this is just this guy. You are going to get w beta of m times the sum for n smaller or equal to m. This is also obvious that n is smaller or equal to n. The sources of n are going to be x, y. And I'm going to get here what I'm going to call nm. So I need to tell you what this is. Nm is going to be the product over x and y of nxy, mxy. So, I mean, at least most of it is obvious. Just maybe why you get that times this, it's just due to the structure of the w beta of n1. You can just check. You know, you're going to get something like 1 over n1 factorial, 1 over n2 factorial. You multiply by n1 plus n2 factorial. You divide by n1 plus n2 factorial, and you get this type of, I mean, really, it's completely straightforward there. If you do it yourself, it's one line. There is no... And 2, well, you can do the same thing. You are going to get also that it's the sum over m, which have a currents asymmetric difference with x and y, of f of m. So this is a little bit analytical of this, but then we are going to dive into the geometry, and you are going to see what you can get with this thing. And here you are going to get the sum for n smaller or equal to m of sourceless current, nm, but there is an indicator that 0 is connected, I mean that x is connected to y in m, an additional factor. This is just a restatement of this one. So now what I need to check, and what it's sufficient to check, is that this quantity, for every m, this quantity is equal to this one. Okay? So fix m, and let's check that. So first thing, if m, if x is not connected to y in m, then this thing is equal to 0. But then this thing as well, because n is smaller than m, so n has sources at x and y, so it has to have a path between x and y. So there is no current smaller than m for which the sources are x and y. Okay? Because otherwise, x will be connected to y in n and a fortiori in m. Both terms are 0. And now if x is connected to y in m, then I need to check that this thing is equal to this one. So now I can forget about this. And I'm going to do it as follows. imagine M, so you have your vertices in G. Imagine M as naturally associated to a multigraph. Okay, and a graph is multiple edges, meaning that between x and y, you put mxy edges. Okay, so x, y, you put mxy edges. So you have a graph like that. It may not be connected. And this is a graph associated to M. Now, what is this quantity, if you interpret like that? Well, this is the number of subgraphs of this graph having no sources in the sense that every vertex is of even degree. You can check. This is exactly this quantity. And this one is the number of subgraphs for which x and y are the only two vertices with odd degree. But now there is a mapping between the number of subgraphs with even degree and the number of subgraphs with odd degree. Just take any path from x to y in your graph and just do the symmetric difference. You take a graph without any, with even degree everywhere. Take the symmetric difference with this path. You get a graph with even degree everywhere except at x and y. And this is, an involution, so it's bijective. So this quantity has to be equal to this one. Okay, so this interpretation gives you the equality. I think it's a cute argument. I mean, that's maybe I didn't convey it very well, but so there is interpretation in terms of subgraphs of, let's say, a big graph M, and then you have an involution mapping the two guys together. I'm not going to write all the details there, but I'm sure that everybody here is able to redo this proof. Okay, what do we do with that now? So let's, this may have looked obscure to you and not so interesting, but you are going to see that we can do many things with it. We are basically going to use it in every proof from now on. So, I asked Michael Eisenman about the intuition behind finding this thing, and it was really, somehow it appeared in the original article of Griffiths because, they were trying, it was really the natural thing to get the inequality I'm going to talk about in a second. But, intuitively, it's not so clear how they got there. So, let's start with a few corollaries. So, for instance, let's look at this quantity. So, you fix G, beta, and x, y in G. What is this thing? Squared. Well, this is, you can look first, there are two partition functions. There is this guy for the first partition function. And since it's square, you can look at it like that by saying this is the denominator in the fraction, right? On the top, I could do the same thing with n1 equal xy and n2 equal xy, and do this thing. Okay? But here, I would like to have the same set of sources. So I'm going to put empty set, and I'm going to notice that if I'm not going to prove the thing because I'm basically proving while stating it. But if I had x, so I should have started with xy here and xy here, right? If I put here xy and xy, then this is just a restatement of what I wrote. Well, it disappeared now, but that this quantity is just the sum sources xy over the sum without sources. So this will be an equality. But now if I apply the switching lemma to xy and to a, which is equal to xy, I'm going to get empty set and empty set because I'm taking the symmetric difference. But I get the indicator that x and y are connected together. So here, if I forget about that, I just need to add indicators that x is connected to y in n1 plus n2. So now you see this is really the interpretation. What is the geometric representation in the context that I introduced before? You want just to define p g beta to be what? To be just the law of the sum, of the trace of two independent sourceless currents. Okay, so this is a trace of sum of two independent sourceless currents. And then you exactly get that if I take this guy squared, it's going to be the probability that that x is connected to y. Okay, so I have, PG beta is percolation configuration. It's a very dependent percolation, okay, because this N1 and N2, these random currents, they are very much correlated. You take the sum of two and so on. But at the end, when I take the square of the correlations, I can rephrase it in terms of connectivity properties of this weird dependent percolation model. So that was the first observation. So, and the proof was basically this scratching and switching lemma. Let me give you two other applications of the switching lemma. These are two inequalities, two important inequalities, which are Simon's inequality and the second Griffiths inequality. So let's start by Simon's inequality, which is saying the following: G subset of ZD, beta positive, and x and y in V of G. Now take a subset, let's call it capital Z, such that to go from x to y using only edges, using only a path for which jxy is strictly positive, I need to go through Z. So typically, let's take the nearest neighbor. For the nearest neighbor model, Z should be a guy which is separating x from y. You need to go through Z to go from x to y. Okay, so let's say I don't want to go into some formalism here, but separating x from y. What do I get? I'm going to get that if I look at sigma x, sigma y, it's going to be smaller or equal to the sum over the z in capital Z of mu g beta f of sigma x, sigma z times the same quantity for sigma z, sigma y. So maybe for those that were present at in the first class, you recognize that this is something that you can deduce from the, from the BK inequality, usually, for percolation. This is somehow reminiscent of the BK inequality. And many of the applications of the BK inequality for Bernoulli percolation, you can get them from this Simon's inequality. So that's why it's a very important thing. I'm going to go back to that later. How do you prove that? Okay, so let's just take this quantity and divide it by this. Okay, so I look at, maybe let me drop, let's just call it mu. And it's divided by mu, mu of sigma x, sigma z. sigma y. So what is it? This is the sum over currents from x to z and currents from z, with sources z and y of w beta n1, w beta n2. And if you think it's divided by the sum of a currents, sourceless current and a current which has sources at x and y. Don't hesitate to interrupt if you have questions, right? Just think, what did I do? I just use, these guys are simple to see. They are just the denominator here, the numerator here, here, and here. And then these guys, because the denominator here, here, and here, they are the same. So I have 2 at the top, 1 at the bottom, so I just get 1 at the bottom. Okay? And now what do? Well, I want to get the same sources at the top and at the bottom, so I'm going to just use the switching lemma to get still the same sources at the bottom. And at the top, I pass this source here. This source is here, so I get the symmetric difference is going to be xy. But this time I'm the indicator of I need what? I need x connected to z in n1 plus n2. Okay? So far, this quantity is smaller than this one, right? This sum is smaller than this one because I'm adding an indicator. But now, what I can observe is that if now I sum this quantity for z in capital Z, what do I get? Here I'm going to get the expected number of point Z connected to X when I do a sourceless current and a current with a point from with sources at X and Y, right? But now, since Z is separating X and Y, and since for N2 I have a source at X and a source at Y, there must be a path from X to Y. This path has to go through one of the points in Z, so this expected number is larger or equal to 1. So this is expected. Connected to X in N1 plus N2. And so this is going to be larger than 1 because Z is separating. And there is an X is connected to Y in N2. So you see, it's once again just proved by observation somehow. There is nothing very deep there. This Simon's inequality is extremely useful. The Simon's inequality is basically the explanation why, for the Ising model, you know how to prove basically everything you know how to prove for Bernoulli percolation, and that you don't know at all for Potts model, random cluster models, or things like that. This inequality is an absolute top. For instance, the exponential decay of correlation for Ising model in subcritical, which I'm going to do later, is really based on this Simon's inequality. That's a good replacement for the BK inequality. So very important inequality. The last corollary I want to mention, but I will not do the proof, I will just sketch it, is that for every G, which is a subset of ZD, for every beta positive, and for every subset A and B included in G, in fact, when I look Here I did 3, but you could do plus, it's the same. It's exactly the same. So if I look at sigma A, sigma B, the product of the two, it's always larger or equal to this thing. And the proof, well, the proof is, once again, just the switching lemma. What you're going to get, when you do the ratio of this over this, you get exactly the same type of quantity as there, except that, of course, instead of xz, you have A. Instead of y, stay with me, zy, you have B. And what you're going to do is just you're going to remove pairs of edges from B. So you start from A and B, you remove 2 edges from B, you get to a bigger A, and you get to something smaller or equal to 1 because of this indicator. So this thing was smaller or equal to 1, right? For instance, you can notice, instead of xz, just take A. So I'm just doing the case where A is any set, and B is a subset of just a pair of points. Then by doing exactly the same proof, you are going to get the smaller or equal to 1. Just you do the switching lemma with A and xy instead of xz and xy, or I mean zy. Sorry. In the more general case, you need to do it several times, but it works as well. Okay, and you always get this inequality. So this can look weird. I mean, this can look useless. But for instance, corollary even. So this is called this is the second Griffiths inequality, and it has a very nice corollary. Is that if you take j smaller or equal to j prime, meaning that you have jxy smaller or equal to j prime xy for every x and y. Then, for every a, you're going to have I'm going to add j to say that here I'm taking the coupling constant j. If I look at the average of sigma a, it's going to be smaller or equal to mu free j beta, g beta and j prime of sigma a. So the bigger the coupling constant, the bigger the correlations, which is something that people always use in ferromagnetic models. But I mean, to prove, in fact, this is the simplest way, because look now what I'm going to do to prove that. I'm just going to differentiate with respect to, say, one coupling constant. So just differentiate. Say, with respect to the coupling constant jxy, the quantity. What you're going to get is, well, maybe I need a 1 over beta here. And what you get is, you can just check, it's a completely straightforward computation. You get this product. Elementary differentiation, but this is positive by this inequality. So the second Griffiths inequality tells you that this is positive, so indeed it's increasing in the coupling constants. Okay. So what I did with 3, I can do with plus. Huh? So remark, ready? All this inequality with plus boundary conditions. Okay, so it remains, I mean, there is one last hour to survive for you. And what I'm going to do now that I kind of set a little bit the framework, I'm going to prove two things. I mean, I'm going to hint how you can prove exponential decay of correlation for the Ising model. So it will be simpler for the people who saw the percolation proof, but at least I will try to give you ideas. I'm not going to redo the proof. And I'm going to prove to you, at least sketch the proof, that that the phase transition is continuous in dimensions 3 and more for the Ising model. Okay. It's 56. We do 5 minutes break, so we start just after just after around the hour.